Okay, today we'll be building an HTTP server from scratch. It's written in a low-level language, Odin. It has manual memory management. We'll discuss the OSI model and operating systems and how that relates to the HTTP protocol. So first, I'll show you our HTTP server, Odin run. And then it's running on localhost, listening on port 49.185. Let's go to Safari, paste that in, hello. If we try a different path, Wazoo, page not found. If we try my super secret page, we get the Lua 5.1 manual. Okay, I'll show you the logs later. For now, let's discuss the OSI model before we go into the implementation. Actually, we'll also discuss the operating systems. Okay, so the OSI model, it's a 7-layer framework that describes how data moves throughout the network. You have the physical layer, the data link layer, the network layer, transport layer, the session layer, presentation, application layer. Now, I'm not going to assume that you have absolutely no idea about the OSI model. I'm just going to give you a general understanding of how the OSI model relates to HTTP servers. And I created a diagram here. Yeah. Yep. I'm too lazy to create a PowerPoint presentation, and I'm too lazy to do editing. So we're going old school. Okay, so I mapped the 5 W's, well, it's the 4 W's and how, to the 7 layers. Okay, how am I going to hold this? Can you see like this? I probably should have planned this better. Yeah, there you go. Oh, let's start with the physical layer. It answers the question what. So, oh, there's hair. What is our data? When it comes to software, we're talking about digital information, but we need to store that information in a physical medium. So what is our data in that physical medium? Is it voltages, radio waves, or light pulses? And the physical layer deals with the NIC when it comes to the hardware. That's the physical medium. Oh, you can't see it. NIC. What does that mean? That is your network interface card. It could be your Ethernet port or your Wi-Fi card. Okay. Next layer, data link layer. This answers who? This deals with MAC addresses. So what are MAC addresses? So your NIC, that is given a globally unique identifier by your manufacturer. That is the MAC address. And the point is so that in your local area network, your device can be identified. So for example, your Wi-Fi router, if you go to the administrator page of your Wi-Fi router, you can see the MAC addresses of all devices connected to it, which is pretty funny, because that way you can find out if the neighbor is riding along your Wi-Fi connection. Okay, and then, so that answers the question, who is connected to the local area network? The next, the network layer, where? Where is the data going to? This deals with IP addresses, Internet Protocol. Now this is similar to the data link layer, but the difference is the scope of it and the fact that it's logical, so it's pure software. So the MAC addresses, they are part of the hardware, they're assigned by the manufacturer. IP addresses are logical addresses. And what this means is they enable hierarchical routing. And this allows it to scale globally to what we call the internet. And when I say hierarchical routing, that means that your router and other routers only need to know routes to other routers. They don't. Whereas if we relied solely on MAC addresses to identify everything, then each router would need to uh, take into account like a billion devices in the world. Okay, so in other words, IP addresses abstract away other networks, and it allows us to route data to other networks. Whereas MAC addresses, this is local only. Next, transport. The transport layer answers how is the data delivered. Okay, and this deals with TCP. TCP means Transmission Control Protocol. This ensures reliable and in order communication, delivery of data between two parties. So if the network layer deals with where the data is going, the transport layer deals with how the data is going to get there to its destination. These four layers is what we call the network stack in the OSI model. And then these top three is the user space stack. And everything here is built on top of this layer, the transport layer. In our implementation, what I mean by implementing an HTTP server from scratch, the lowest that will go is the TCP server. Okay, because technically, if we're being vague, you can also implement an HTTP server from scratch, starting with creating Wi-Fi cards. Okay, so no, we'll only create first a TCP server, and then we'll build an HTTP server on top of that. Okay, so what do I mean by the user space stack builds on top of this TCP layer, transport layer? Okay, so the transport layer, this is how we send raw data, but that means nothing. Through the wire, that's just bits, bytes. It has no meaning. So what we build on top of that is what gives this data meaning. So first of all, session. That is where HTTP comes in, where you'd have long-lived connections. Now, this is a TCP server, so there's also connections here, right? So why wouldn't this be in the session layer? Okay. The difference here is that the session layer gives semantic context to the long-lived connection. So for example, you're in a multiplayer video game lobby. Are you in the loading screen, in the champ select screen, in the you're in the match itself, or you're in the final result? You can communicate that using HTTP. Whereas with TCP, all you can really tell here is, do you have a connection with another host in some other network? Okay, and then you'd also have here TLS and SSH. So this is for HTTPS, encrypted connections, and SSH. Okay, presentation layer. This deals with how the data is formatted. This covers encoding, compression, and also encryption. So this would be your tar archives, your JSON files, your protobufs, your Huffman encodings. And it's important to know that in this diagram, there is clear separation between the layers, but in implementation, the applications would do a little bit of multiple layers. So for example, the SSH or TLS, that covers both presentation and session. Okay. And then for NIC cards, they can do some work for the data link layer on the firmware itself. Okay. DNS application layer, that's the topmost layer. This is where we refer to the DNS servers or the browsers. So your browser is just making the HTTP request for you. So when you go to a website, it goes way down to this transport layer. It opens a TCP socket to that server. It creates the HTTP message and then communicates. DNS, that's what gives websites this human readable output. So if let's go back to the website here. You see, I connected to my website through an IP address, and then there's a port. So that is how servers work. But for your user-facing website, you'd have a user-readable name like Google. Okay, so that's the job of DNS servers. They give these IP addresses names. Okay, I'm gonna cut that out. I just switched to the terminal and it showed you accidentally the logs for the website. Okay, let's go back. And I actually forgot to mention something. Actually, two things. I want to discuss more about IP and TCP. Oh, you can't even see it. Okay. Like I said, TCP sits on top of IP. IP, network layer, deals with sending data where it needs to go. It doesn't care about whether that data gets there successfully or its integrity is preserved. That is the primary responsibility of the transport layer. When data packets leave this IP address, this host, and reaches its destination, another host on another network, aka another IP address, TCP takes over. Now, since this is another host, multiple processes, applications can listen on it. You'd need some way to differentiate those multiple applications. That's where ports come in. So port 49163, that represents my server, and then another port would represent your Postgres server, another port would represent some other service, and then there's going to be ports that are dedicated to HTTP connections, TCP, yada yada yada. This combination of the IP address and the port is a unique identifier, and that's what identifies the processes that listens on these hosts. When data arrives at that destination and initiates a connection, there's this thing that happens. It's called the TCP handshake. The client, this is the client, this is the server. The client sends an initial request or message. It's called a synchronization message, SYN. The server must reply with SYN acknowledged. Okay. Finally, the client must respond with a final acknowledged. Now, if they don't receive any of these messages successfully, then we don't have a successful connection. So that's the first part of TCP, ensuring that there is a reliable communication between two parties. And then, for ensuring the integrity of data, it does checksums on the data. And multiple layers of the stack does checksums on the data. So there's continuous verification of the integrity throughout the stack. And to ensure that data is received in order, TCP uses sequence numbers on the packets so that when packets come out of order, and they will, TCP can reconstruct the message again. Okay? that covers the OSI model. Now, let's move on to operating systems. Actually, I don't know why I put away my whiteboard. Okay, let's erase this. I've mentioned Syscalls. So let's talk about what Syscalls are and what their role is in operating systems. I'll have to draw another diagram. How would I do it? Here you go. An operating system abstracts away the hardware. It virtualizes it to logical counterparts so that multiple processes can share this single device, and they only have to worry about their single piece of the pie. When I say virtualizing the hardware, I mean virtual memory, so that each process only has its own address space. That's why in a low-level language with manual memory management like C, when you go out of bounds in your array, you're accessing memory outside of your assigned address space. And that's why you get a segmentation fault. Okay, I drew a diagram here to represent the stack. You have the hardware, you have your kernel, the operating system, and then the user space. The kernel is part of the operating system. It's the core part, actually, of the operating system, and it's what directly interfaces the hardware. When I say hardware, I mean your actual computer, your NIC, your Wi-Fi, your keyboard, your hard drive, your CPU, your RAM. OS, that's going to be Linux, Mac OS, Windows, user applications, your web browser, your photo editor, your video editor, your screen recorder, your video games. Technically, you can consider a large part of the operating system as user space applications too, like CLI utilities, but you consider them part of the operating system. So now, kernel, since it's the one that directly interfaces with the hardware, it's the most privileged part of your system. I'll give you a fun fact. If you're not updated, there is a huge controversy in online video games because they use kernel level anti-cheats. Looking at you, Valorant, Riot. Yeah, so Riot uses an anti-cheat that lives in the kernel. So it can monitor all activity in your hardware. And you don't have to be a software developer to understand how crazy that is, just from a privacy perspective. But if you're a software developer, you understand that even without the privacy concerns, that is a crazy thing to do because you're taking video code from a video game company and putting it in the kernel. And when all software right now is shit and their game is full of bugs, I don't want that, man. Anyway, that's rant over. When a user application does I/O operations, like listening for user input from the keyboard or listening to a socket, interacting with the NIC, it needs to talk to the hardware, aka through the kernel. To formalize this process, the kernel exposes OS primitives called Syscalls. Let me write that down. Syscalls is how a user space application can drop down to kernel level privileges and specifically request certain services from it. To create our TCP server, we need to use a couple of syscalls. You need socket, bind, listen, and accept. Yes, okay. Let me add the parentheses. Socket is what creates the socket, the logical socket. Then you bind it to an IP address plus a port, and then you start listening for connections there. And then once a new connection comes in, you need to accept it. Accept returns a socket descriptor, and then you treat that like a normal file descriptor. You can read and write data to it, and that's how you do communication using TCP sockets, aka TCP servers. Okay, I think you have enough context now on the whole network stack, so we can go to the implementation now. Yeah. Okay. Switch, go to Ghosty, and Vim, TCP Odin. Let's start. So here first, I just have some wrapper functions because I'm using the intrinsics package instead of the core library here in Odin, since we are using the syscalls directly. Our first syscall is going to be the socket syscall. Here you go. And you can create different types of sockets here. Like I mentioned earlier, there's the UDP and Unix sockets, and it takes 3 arguments. And I hard-coded the arguments here. So there are 2 questions. How did you figure out what arguments this syscall gives or takes, and how do you know the values to put there? Well, we can read the man page for socket, and you'll see that it takes 3 arguments: domain, type, protocol, and they're all integers. And then when you read the description, it indicates the values that are valid there for domain. These are the values. And what did I use? I used PF inet, okay? And I set it to 2. So how did I figure out that PF inet is 2? You need to reference your system libc. I have a command here. I'm on Darwin, so mine is going to be quite different to those on Linux. And then we go here. This outputs all the macro definitions in that specific header file of libc. And let's search for pf inet. Okay, it's defined as af inet. So let's search for af inet now. Okay, af inet is set to 2, and that's how we get the value of 2 for pf inet. Yeah. And then you do the same thing for all other values. Moving on. I'll go straight here first, and then you'll figure out that you need to do bind so that you can bind your IP address to the socket. If we look at the man page for socket, or bind rather, here you go. It takes in an integer, which is the socket descriptor. Oh, I forgot to show you that in socket, in these man pages, it also shows you the return value. So for the socket syscall, it returns -1 if an error occurs, and then it returns a descriptor on success. Okay, going back to bind. Oh, bind. There you go. It's a bit claustrophobic. It takes in a sock adder as a second argument, and then what I actually use here is the sock adder in. I'll explain why. So if we look, if we go back here, where is it? Now instead of socket.h, we need to go to types.h, and then if we look for a socket or sock adder, where is it? Readme. Just go back here. Just cd into here. Yeah. And we will search sock adder for the type. Oh. Here you go. I found it. So the struct adder takes in a 14-byte character array as its third field. And this tells you that this is actually just a general, a generic struct, and that different implementations would have a more specific struct or type that can break down this 14-byte character array into separate fields. And this is something that you just have to know. Maybe you can ask ChatGPT. That's what I did. And instead, you'll use the specific struct, the sock adder in. There you go. Here we go. So this is in net inet in .h. Okay. And then this is the actual type of struct that you need to pass into bind. And that's why here in TCP Odin, that's why I started creating the address after the socket. Okay, here I just used the standard library. I couldn't be bothered to actually create the struct using the C types in Odin. And then to finish the initialization of this struct, you need to use this function, the inet piton, presentation to number. It converts your string representation of the IP address into its integer equivalent. You see here, there's the synaddr field of the address struct, and it mutates this through this out parameter. Next, we'll bind the socket to the address that we just created. And you'll see that before I bind it, I set an option on the socket descriptor to reuse the address. What this does is now when we immediately restart our server after shutting it down, we can use the address again instead of there being like a 10-second, 15-second delay, which is going to be annoying for local development. And then you get the socket name. So earlier I had the port set to 0, which would let the OS pick. And if you do this, you need to do get socket name so that the address can be filled in with the proper port that the OS chose, so that you can print it later on. And then you listen. Now this is going to start accepting connections in the background. So this is multi-threaded by default. And then to actually get the socket descriptor for individual connections, you'd have to do where is that? You'd have to do the accept syscall here. Okay, and then we convert it into an OS handle, and then that's our file descriptor, aka socket descriptor. And then we just interact it normally using the IO library here. There you go. And then you also have to remember to close it. And if you're handling multiple connections, you'd have to do this dot accept on in the for loop as well, and then you do non-blocking IO. Okay, so let's run this again, and I will, no, actually not again. This is the first time I'm running this, the TCP file. And then we create a client. So NC, that's netcat, NC help. This is way too, okay, NC means netcat, all right? And then we connect to our server on port 6969. And now everything that I type in here will get sent to our server. So ARST, you said ARST. What did we do? We read the data and then we printed it out. Okay. Hello. Can you hear me? Me. Okay, that's enough demo. Now let's go on to the HTTP server. So the HTTP server is just a format that built on top of TCP. So you see that TCP is just sending the raw data. It's up to us to give structure or semantic meaning to that data. And so for here, we need to start creating HTTP messages. Now we need to go back to Safari, and we need to reference the HTTP spec. Here you go, HTTP 1.0. And you'll see that, let's go to, HTTP message. There you go. This is the format that we need to follow if you want to create a valid HTTP message. So there's a request line, and then your headers, and then the body. And these are all separated by a CRLF. That's a a carriage return line feed, which is this. Two escape bytes, \r, \n. Okay, and then you just read on through this. So first you'd have the request line. The request line would be this. Yep, you'd have the method and then the request URI, and you really just follow this to the T. You can read my code for the implementation. Let's go back to GoC. See here, we take in the data for the message from the client, we read it, and then we parse it. We start parsing it. If it's a GET request, we do this. We switch on the request URI. There you go. Where did I start parsing it? Here we go. HTTP parse request. If we go to this function, HTTP parse request, there you go. I start parsing the HTTP message. Yeah. I'm not going to go through all of this because it's really just about reading the spec and reading the code and how to do it. And then to reply, we just create a valid HTTP message too. So going back to Safari, to create a response, it has a similar shape to the request message. There you go. And I just hard coded it here. You create your response line, not found, which is the phrase, and then content type, content length, and then here is your actual body separated by two carriage return line feeds. Okay, so you saw earlier that when I did my super secret page, we loaded the Lua documentation. So here I have the Lua file, the Lua repository rendered, and then I just loaded that HTML file during compile time, and then I wrote that out to the socket descriptor. Okay. So again, when we do Odin run HTTP Odin, then we create a new file. Let's first try the curl. Let's curl onto it. 127.0.0.1 49.200. Hello. If we try wazoo, page not found. You see here that if it's not an actual URI that I support, I return page not found. Yep. And then my super secret page. You see, so it's just literal bytes that we're sending to each other. And then the web browser's job is to render that into a GUI. Okay. So you see here, we're getting warnings that the client is using HTTP 1.1. So we need to do, I have notes here. Let's check my notes again. Curl, there you go. Wait, I didn't put it here. Well, anyway, there's a way to make this use HTTP 1.1. Let's see if I can remember it. 10. Here we go. We did, let's not do this. Okay. We passed the 1.0 flag, and now we're not getting the warning. You see here, I did a warning, HTTP warning. If the version of the request is not 1.0, we log. So now when we go to the browser, Safari, and we go to this again, and what was the port? It is 49.200. Easy to remember. 49.200, and then we go to my super secret page. I'm not gonna type this out. Super, okay. Safari. Oh, what? Oh, it's because of my extra. There you go. If you look at the logs, go see. Yeah, we got a bunch of warnings because the web browser always uses HTTP 1.1. And I want you to notice that, let's go back to Safari. When we had doubled slashes here, it did not clean the path automatically so that it just becomes one slash. So it becomes a page not found. So that's one of the things that your HTTP frameworks do under the hood. It cleans the path. It turns consecutive slashes into a single slash. Yep. There you go. So that is how to create an HTTP server from scratch. It's only 200 lines of code. And if you want to do a TCP server from scratch, it's only 90 lines of code. Links to the repository is in the description. I hope you learned something today. That's it. Oh, and don't forget to drink water.